my name is Naina and I'm from the Buddhi Academy. So today we'll see the last part of the chapter, that is chemical bonding and molecular structure. In this, the last part is the molecular orbital theory or the MO theory or MOT. So let's start with the molecular orbital theory. The theory was developed by F. Hunt and R.S. Mulligan in 1932. Now, what are the features of molecular orbital theory? On what basis does this theory develop? Okay. The first point is the electrons in a molecule are present in the various molecular orbitals as the electrons of atoms are present in the various atomic orbitals. Now, in our last video we have seen about hybridization, right? So we get hybrid orbitals. Most of the hybrid orbitals are molecular orbitals. So based on that, a molecular orbital theory was given. Now here, the electrons in a molecule are present in various molecular orbitals. Now as the electrons of atoms are present in various atomic orbitals. Now each atom has atomic orbitals. When you combine two or more atoms together, you form a molecule. Now the electrons which are present in a molecule, they are present in the molecular orbitals. Okay, and the ones which are present on atoms are present on atomic orbitals. Now, the atomic orbitals of comparable energies and proper symmetry combine to form a molecular orbital. Now you know, in hybridization, as I told you, the energies of the orbitals should be similar to form an hybrid orbital. Same thing, the atomic orbital which combine together should have a comparably same energy and a proper symmetry so that they can combine and form a molecular orbital. Now, third point is when an electron in an atomic orbital is influenced by one nucleus in a molecular orbital, it is influenced by two or more nuclei depending upon the number of atoms in the molecule. Now, when electron in an atomic orbital, okay, in an atom you have only one nucleus of that particular atom and the electrons are influenced by that nucleus. But whereas in molecular orbital, the influence on the electrons are made by two or more nuclei because a molecule contains more than two atoms, two or more than two atoms involved in that, right? So the nucleus of both the atoms, they influence the electrons in that molecule. Okay, thus an atomic orbital is monocentric while molecular orbital is polycentric. Why atomic orbital is monocentric? Because it has only one nucleus in the center, whereas molecule is a polycentric thing because it has two or more nucleus and each of the two or more atoms and each of those atom has different nucleus to it, so it has polycentric nature. Now, the number of molecular orbitals formed is equal to the number of combining atomic orbitals. So how many molecular orbitals are formed is simple. The number of combining atomic orbitals, how many number of atomic orbitals are combining, that many number of molecular orbitals are formed. As I told you in hybridization, how many number of atomic orbitals are hybridized, that many numbers of hybrid orbitals are formed, and those hybrid orbitals in short are molecular orbitals. Okay. Now when two atomic orbitals combine, two molecular orbitals are formed. So two atomic orbitals, when they combine, how many molecular orbitals are formed? Again, two molecular orbitals are formed. One is known as bonding molecular orbital and other is known as antibonding molecular orbital. So there are two kind of molecular orbitals which are formed. One is bonding molecular orbital and second one is the antibonding molecular orbital. Okay, now the bonding molecular orbital has lower energy and hence greater stability than the corresponding antibonding molecular orbital. Now, regarding energy and stability, bonding molecular orbital has lower energy and hence they are greater in stability. Since they have low energy, their stability is also greater corresponding to their antibonding molecular orbital. So if bonding molecular orbital has lower energy and greater stability, then antibonding will have higher energy and low stability. Okay. Just as electron probability distribution around a nucleus in an atom is given by atomic orbital, the electron probability distribution around a group of nuclei in a molecule is given by a molecular orbital. Now, how the electrons are arranged in the atomic orbital in an atom? Okay, in an atom, what will happen? Surrounding the nucleus, you have electrons arranged, right? That 2 and 8 from it. Octet, they form an octet, right? So similarly, the probability distribution, how the electrons will be distributed around the nucleus in a molecule, is given by your molecular orbital. Okay. The molecular orbitals, like atomic orbitals, are filled in accordance with the Aufbau principle, obeying the Pauli's exclusion principle and Hund's rule. So the molecular orbitals are also filled according to the Aufbau principle. Okay, obeying the Pauli's exclusion principle and Hund's rule. So these are the pattern which is followed. How atomic orbitals are filled, like how they are filled. 1s is filled first, then 2s, then 2p, 3s, 3p, 4s, 3d. There is an order which is followed by Aufbau, right? And this order was made according to Pauli's exclusion principle and Hund's rule. So similarly, molecular orbitals are also filled according to the Aufbau principle, obeying Pauli's exclusion principle and Hund's rule. Okay. Now, next is the formation of orbitals, that is linear combination of atomic orbitals, or LCAO. What is LCAO, why this was found, or why this was put forth, we will see here. Now, according to wave mechanics, the atomic orbitals can be expressed by wave function psi, okay, which represents the amplitude of the electron waves. Now, as you know, everything we say that light, for that matter sound, everything has dual nature, right? Light has a particle nature as well as a wave nature. Here also they have compared the atomic orbitals. Okay, they have a wave function which is represented by psi, which represents the amplitude of electron waves, the energy that is released by electrons, or that is gained by electrons. Okay, those energies, they are depicted in electron waves, and that electron waves, they have given a wave function psi to it. Now these are obtained from the solution of Schrödinger wave equation. Now from where they have obtained this? They have obtained it from Schrödinger's wave equation. Now however, since it cannot be solved for any system containing more than one electron, molecular orbitals which are one electron wave function for molecules are difficult to obtain directly from the solution of Schrödinger wave equation. Now Schrödinger wave equation for electrons, for atoms, it applies only for the system that contain one electron. But molecules, you know, molecular orbitals which are one electron wave function for molecules are difficult to obtain, because molecules have more than one electrons, right? So here you cannot obtain any solution from this Schrödinger wave equation. Now to overcome this problem, an approximate method known as linear combination of atomic orbitals, or LCAO, has been adopted. Now to overcome this issue, now because Schrödinger wave equation cannot solve the problem, so to solve that issue, they have put forth this concept of linear combination of atomic orbitals, or LCAO. Now what is this LCAO? Let us apply this method to a homonuclear diatomic hydrogen molecule. So with an example you will understand it better, like what this concept means. So here they have taken an example of diatomic hydrogen. Diatomic hydrogen means your simple H2 molecule. Okay, now consider hydrogen molecule consisting of two atoms, A and B. Now again same, you have to split this hydrogen into two. Take one as A, another one as B. Okay, now as you know, hydrogen, they have only one electron in them. Okay, so they have 1s1, right? So each hydrogen atom in the ground state has one electron, that is 1s orbital, right? Now the atomic orbital of these atoms may be represented by the wave function psi A and psi B. Hydrogen molecule, they have one electrons, you can apply the wave function here. So for hydrogen A, it is psi A, and for hydrogen B, it is psi B. Now, mathematically, the formation of molecular orbitals may be described by the linear combination of atomic orbitals that can take place by addition and subtraction of wave functions of individual atomic orbitals as shown below. Now, why we use LCAO? It is basically to represent the formation of molecular orbital in a mathematical form. Okay, so mathematically the formation of molecular orbitals, it can be described using linear combination of atomic orbitals or LCAO. How you can do that? You can do that by addition or by subtraction. Addition and by subtraction of wave functions. Okay, these wave functions, you can either add them or subtract them to find the formation of atomic orbital mathematically. Now, therefore, the two molecular orbitals, that is sigma and sigma star. Now, what is sigma and sigma star? You know, there is a bonding and anti-bonding molecular orbitals are formed, right? Bonding and anti-bonding. Now, sigma stands for bonding molecular orbitals and sigma star stands for anti-bonding molecular orbitals. Now, for sigma, you have to add both the psi functions. Okay, that means for bonding molecular orbitals, you have to add both the wave functions, and for anti-bonding molecular orbitals, you have to subtract both the wave functions. Now, the molecular orbital sigma is formed by the addition of atomic orbitals and is called bonding molecular orbitals, as I already explained to you. So, sigma is for the bonding molecular orbitals, and to find the sigma bond, you have to add both the wave functions, while the molecular orbital sigma star is formed by the subtraction of atomic orbitals, and this is called as antibonding molecular orbital. Now, how you will represent the molecular orbitals? Now, this is the molecular orbital diagram. Here you have to add an increasing energy level. Okay, for each of them you have to show. Now, here psi A means your hydrogen A, psi B means your hydrogen 2, that is Hb. Both of them are having 1 electrons. Okay, now both of the electrons, when you add them, they will form your bonding electron, that is your sigma bond, right? Bonding orbital lower energy than that of the atomic orbitals. Okay, so you added both the electrons and you formed your bonding orbital. Now, for anti-bonding molecular orbital, you have to subtract. Now, 1 minus 1, it is 0. So, no orbital, no electrons are present here. So, this is your anti-bonding molecular orbital. Okay. Now, these are your atomic orbitals and these are your molecular orbitals. Okay. Qualitatively, the formation of molecular orbitals can be understood in terms of constructive or destructive interference of the electron waves and combining atoms. Now, in short, you can say that qualitatively, okay, the formation of molecular orbital is understood by a constructive and a destructive interference. Now, which is the constructive? Bonding is your constructive and anti-bonding is your destructive, because here you are pairing up both the electrons and you are constructing a bond. Here both the electrons are cancelled off, so here you are destructing it. So, in formation of bonding molecular orbitals, okay, the electron waves of the bonding atoms reinforce each other due to constructive interference. As I told you, they are constructing themselves. So, bonding molecular orbital, they are constructive interference, while in the formation of antibonding molecular orbitals, the electron waves cancels each other due to destructive interference. Okay. Now, as a result, the electron density in the bonding molecular orbital is located between the nuclei of bonded atoms, because of which the repulsion between the nuclei is very less, while in case of antibonding molecular orbital, most of the electron density is located away from the space between the nuclei. Now, why this constructive and destructive forces or interference takes place? Now, the electron density, okay, of the bonding molecular orbital is located between the nuclei. There are two nuclei, right? One of the hydrogen and second hydrogen. There are two nuclei. So the electron density, that means most of the electrons are present in between both the nuclei. Now, because the electrons are present between the nuclei, there is less repulsion which is faced by the nucleus. You know, right? Nuclei both are positive, so they will repel each other. When they are close, they will repel each other. But when we place an electron in between them, or when we increase the electron density between the nuclei, what will happen? There will be attractive force between nucleus and the electrons, so there will be less repulsion. And when you reduce the repulsion, the nuclei will be more stable. So hence, lower the energy, stable is the bonding molecular orbital. But whereas in antibonding molecular orbital, what happens is, between the nuclei, the electron density is less. Okay, the electrons are placed further away from the nucleus. So hence, there is a repulsion which is faced between the nucleus, which increases the energy and the stability is reduced. Okay, so this is the reason in antibonding there is a destructive force, whereas in bonding there is a constructive force. Now, in fact, there is a nodal plane on which the electron density is 0. So there is another plane called as nodal plane where the electron density is 0. That means there is no electron between the nuclei, and hence the repulsion between the nuclei is high. Okay, and that is mostly seen in antibonding molecular orbitals. Now, electrons placed in bonding molecular orbital tend to hold the nuclei together and stabilize the molecules. So again, same thing, the electrons which are placed in bonding molecular orbitals, what they do is they hold the nuclei together and try to stabilize the molecule. Therefore, bonding molecular orbital always possesses lower energy than either of the atomic and the atomic orbitals that have combined to form it. So the atomic orbitals which are combining to form the molecular orbital, both of them separately will have higher energy, but when they combine together, what happens is the nuclei of both the atoms, okay, they are held together by the electrons, hence thereby reducing the energy. Okay, and when the energy is reduced, the atomic orbitals, the molecular orbitals, they have a higher stability compared to their single atomic orbital form. Now, in contrast, the electrons placed in the antibonding molecular orbital destabilize the molecule. This is because the mutual repulsion of electrons in this orbital is more than the attraction between the electron and the nuclei, which causes a net increase in energy. Now, what happens in antibonding molecular orbital? They have a destabilized molecule. Okay. Now, why they have a destabilized molecule? This is because the mutual repulsion. Okay, there is a mutual repulsion between the electrons. There is electron repulsion, which is greater than the attractive force between the electron and the nuclei. Okay, which causes a net increase in the energy. It may be noted that the energy of the antibonding orbital is raised above the energy of the parent atomic orbitals that have combined, and energy of the bonding orbital has been lower than that of the parent orbitals. Now, since atomic orbitals are combining together to form the molecular orbitals, atomic orbitals are considered to be parent atomic orbitals. Okay. Now, the energy of the parent atomic orbitals and the energy of the antibonding orbital. Okay, the energy of the antibonding orbital is raised. Raised means it is more than the parent atomic orbital ka energy level. Okay, parent atomic orbital means you're combining atomic orbitals. The energy of those combining atomic orbitals is less than the energy which is obtained by the antibonding orbitals. Okay. Now, the total energy of the two molecular orbitals, however, remains the same as that of two original atomic orbitals. But combined together, both bonding and antibonding molecular orbitals, when we combine together, their energy level remains same as that of their original atomic orbitals. Okay. So this is what our LCAO concept is used for. Now, second thing is the conditions for the combination of atomic orbitals. What are the conditions that are put forward for the combination of atomic orbitals? Now, the linear combination of atomic orbitals to form molecular orbital takes place only if the following conditions are satisfied. Now, the LCAO concept of molecular orbital, it applies only when these conditions are satisfied. Now, what are the conditions? First one is the combining atomic orbitals must have same or nearly the same energy. Again, the combining atomic orbitals, they should have a same or nearly a same energy level. This means 1s orbitals can combine with another 1s orbitals but not with 2s orbitals. Okay, that which means, in short, you can combine the atomic orbitals with same or nearly the same. Now, the same means 1s can combine with 1s, 2s can combine with 2s. Okay, nearly the same means 2s can combine with 2p. Okay, so these are the same or nearly same energy levels. Okay, but you cannot combine 1s with 2s or 1s with 2p, or for that matter 2p with 3s. Okay, because the energy of these orbitals is appreciably higher than that of the other orbitals. For example, 2s and 1s, you can't combine these two orbitals because the energy of 2s orbital is comparatively higher than that of the 1s orbital. This is not true if the atoms are very different. Okay, if the atoms are very different, then this is not applicable for them. Okay, now second condition is the combining atomic orbitals must have same symmetry about the molecular axis. Now they should have same symmetry. For example, by convention, z-axis is taken as the molecular axis. So z-axis is considered to be the molecular axis. Now it is important to note that atomic orbitals having same or nearly same energy will not combine if they do have the same symmetry. If they do not have a same symmetry. If your energy levels are same, for example 2s, 2p, energy level is nearly same, they will combine only when you have a similar symmetry. If they doesn't have a same symmetry, that means if they doesn't follow the molecular axis, they won't be combining. Okay, so to combine, they should have same or nearly same energy level, and they should have a same symmetry along the same axis. Okay, now for example, 2pz orbitals of one atom can combine with 2pz orbital of other atom, but not with the 2px or 2py orbitals because of their different symmetries. Okay, so here you can combine both the 2pz orbitals of different atoms. Okay, 2pz orbital of one atom and 2pz orbital of another atom. You can combine them together, but you cannot combine 2pz of one orbital and 2px or 2py of other orbitals because all the three are in different symmetries. Different symmetries means all the three are in different axes. For example, this is your x-axis. Okay, this is your y-axis, and from the center goes your z-axis. From the center goes your z-axis. Okay, so all the axes are in different directions, right? All the axes are in different directions. This is y, this is x, and this is z. Now, if one orbital is here and second orbital is here, can you combine both of these orbitals? They will be combining in a different angle, right? There won't be any symmetry in them. So for this matter, you cannot combine x-axis or y-axis with z-axis. Only z-axis will pair with z-axis, x-axis will pair with x-axis. So the symmetry of the orbital should also be taken into consideration when there is a bond formation in molecular orbitals. Now, next point is the combining atomic orbitals must overlap to the maximum extent. So the combining atomic orbitals, the overlapping between them should be maximum. Okay, so greater the extent of overlap, the greater will be the electron density between the nuclei of the molecular orbital. So the greater extent of overlapping, the greater will be the electron density and stronger will be the bond, okay, or molecular orbital. Now, if all these conditions are satisfied, then only the LCAO combination of atomic orbitals is taking place, or on if it follows these three conditions, then only the molecular orbital will form using the LCAO concept. Now next is the types of molecular orbital. What are the types of molecular orbitals? Now molecular orbitals of diatomic molecules are designated as sigma, pi and delta, etc. So there can be various orbitals that can be formed, sigma, pi, delta, etc. Now in this nomenclature, the sigma molecular orbitals are symmetrical around the bond axis, while pi molecular orbitals are not symmetrical. So here basically we will see sigma and pi molecular orbitals. So sigma molecular orbitals are formed when they are symmetrical around the bond axis, whereas pi is formed when there is no symmetry or it is non-symmetrical. Okay, for example, the linear combination of 1s orbitals, okay, centered on two nuclei produces two molecular orbitals which are symmetrical around the bond axis. Now, for example, if you combine 1s orbitals, okay, since both of them are same, you will form a symmetrical bond around the axis. Okay, now such molecular orbitals are of the type sigma, okay, and are designated as sigma 1s and sigma star 1s. Okay, since they are forming bonding molecular orbitals and they have a symmetrical structure around the bond axis, so they are sigma, and we will depict them. Since we have used 1s orbital and the bond formed is sigma, we will designate them as sigma 1s, and for antibonding it will be sigma star 1s. Okay, now if internuclear axis taken to be in the z direction, it can be seen that a linear combination of 2pz orbitals of two atoms also produce two sigma molecular orbital designated as sigma 2pz and sigma star 2pz. Now as I told you, in combination or in LCAO, the molecular axis, okay, we consider z axis to be the molecular axis. So in this case, the internuclear axis, that is in z direction, okay, in the z axis you can consider the 2pz, okay, 2pz to form two atoms, okay, 2pz orbitals of two atoms to form a sigma molecular orbital designated as sigma 2pz and sigma star 2pz. Okay, now the molecular orbitals obtained from 2px and 2py orbitals are not symmetrical around the bond axis because of the presence of positive lobes above and negative lobes below the plane. Now why 2px and 2py are not considered to be molecular axis is because they are non-symmetrical. Why they are non-symmetrical? Because both of them, okay, both of this axis have the presence of a positive lobe above and a negative lobe below the molecular plane. Such orbitals, they are labeled as pi orbitals, okay. So 2px and 2py are labeled as pi orbitals and given as pi and pi star. Now why pi? The ones which are formed on the bonding molecular orbitals, okay. You have a pi bonding molecular orbital which has a larger electron density above and below the internuclear axis. The antibonding or pi star antibonding molecular orbitals has a node between the nuclei, okay. Now the energy level diagram for molecular orbitals. What are the energy level diagram and how we can draw them? Now we have seen 1s atomic orbitals on two atoms form two molecular orbitals designated as 1s, sigma 1s and sigma star 1s. We have seen that in the top part. Now in the same manner, 2s and 2p orbitals, okay, 8 atomic orbitals on two atoms give rise to the following 8 molecular orbitals. So in short, you get 8 molecular orbitals, okay. 1, 2, 3, 4, 5, 6, 7 and 8. So 2s and 2p all together you get 8 orbitals. Okay, amongst them 4 are antibonding molecular orbitals and 4 are bonding molecular orbitals. So these are the energy level diagrams. Okay, and this is for 2px, this is for 2pz, and this is for 1s. Okay, they have shown for different orbitals. For 1s you can see there is an bonding sigma molecular orbital and anti-bonding sigma molecular orbital. One is bonding and another one is anti-bonding. Okay, so this is anti-bonding molecular orbital, this is bonding molecular orbital. Again same here, this is anti-bonding, this is bonding molecular orbital. There is a nodal plane, this is a nodal plane. Okay, so this is anti-bonding and again this is bonding. Now the energy levels of these molecular orbitals being determined experimentally from spectroscopic data for homonuclear diatomic molecules of second row elements of the periodic table. Now how the energy levels of these molecular orbitals are obtained? They are obtained spectroscopically from the homonuclear diatomic molecules which are present on the second row. For example, here all your H2, N2, O2, C2. Okay, now the increasing order of energies of various molecular orbitals for O2 and F2 is given below. Now this trend will be followed only by O2 and F2 molecules. Okay, now difference, I'll tell you what is the difference. Here you can see, okay, this is followed by O2 and F2 and this series is followed by other molecules. However, this sequence, okay, the above sequence of energy level of molecular orbital is not correct for the remaining molecules. Okay, like L2, B2, Be2, C2, N2. Okay, all these molecules except O2 and F2, they doesn't follow this sequence. Okay, so for instance, it has been observed experimentally that for the molecules such as B2, C2, N2, etc., the increasing order of energies varies molecular orbital is this. Okay, now what is the difference between both of the series? Now here you can see that after the anti-bonding 2s orbital you have a bonding 2pz orbital. Okay, after bonding 2pz orbital is your bonding 2px and 2py orbitals. Then you have anti-bonding 2px, 2py and anti-bonding 2pz orbital. This is what O2 and F2 follows. Whereas other molecules, you can see here that after sigma or after anti-bonding 2s orbital, you don't have this 2pz here. Here you don't have the 2pz. Instead of 2pz, what you have is your bonding 2px, 2py. After bonding 2px, 2py is your bonding 2pz, and the remaining thing continues as it is. So the basic difference is in O2, F2 and other molecules is in O2, F2 your sigma 2pz comes first, then your 2px and 2py. Okay, now the important characteristic features of this order is that the energy of sigma 2pz molecular orbitals is higher than that of 2px and 2py molecular orbitals. Okay, now the electronic configuration and molecular behavior. The distribution of electrons amongst various molecular orbital is called the electronic configuration of the molecule. Electronic configuration, you know what it is. Now from the electronic configuration of the molecule, it is possible to get important information about the molecule as discussed below. Now what are the important information? First one is the stability of the molecule. If Nb, that is number of bonding, is the number of electrons occupying bonding orbitals. Okay, Nb is the number of electrons in the bonding orbitals and Na is the number of electrons occupying the anti-bonding orbitals. Okay, now this Na and Nb you have to remember. The stability of the molecule, how it will tell you? First thing is the molecule is stable if the number of bonding electrons is greater than the number of anti-bonding electrons. If number of bonding electrons is higher than the number of antibonding, then your molecule is stable. The molecule is unstable if it is opposite. If the number of antibonding is more than the number of bonding, the molecule is unstable. Now, more the bonding orbitals are occupied, and so the bonding influence is stronger and a stable molecule and the result is stable molecule. Okay, if more the bonding orbitals, then the antibonding, the influence of bonding molecular orbital is stronger and stable molecule results. Okay, and a result of stable molecule is attained. Now, if the antibonding orbital are occupied more, then the influence is stronger for antibonding, and therefore the molecule is unstable. Now, next is your bond order. The bond order is defined as the half difference between the number of electrons present in the bonding and the antibonding orbitals. Now, how you will calculate the bond order? Bond order, you have to calculate it as half of the number of bonding minus number of antibonding. Okay, or NB minus NA divided by 2. So, this is the formula for bond order. Now, the rules discussed above regarding the stability of the molecule can be restated in terms of bond order as follows. Now, the rules about stability which we have seen, we can rearrange them in the form of bond orders. Now, a positive bond order is attained when you have more number of bonding than the antibonding. If you have more number of bonding, then a positive bond order is attained, which means a stable molecule is there. If you have a negative bond order or a zero bond order, then that means you have an unstable molecule. That means your number of bonding is less than number of antibonding, or both number of bonding and number of antibonding is equal to each other. In these two scenarios, you get a negative or a zero bond order, which means your molecule is unstable. Okay. Next is nature of the bond. Now, integral bond order values 1, 2 or 3 corresponds to single, double and triple bonds respectively as studied in the classical concept. Now, nature of bond, say single, double or triple bond, what we have seen in your classical concept. Next is the bond length. Now, the bond length or the bond order between two atoms in a molecule may be taken as an approximate measure of the bond length. Now, the bond length decreases as the bond order increases. Now, bond length means the bond order. Okay, the bond order between two atoms. Okay, we can consider that to be the approximate measure of the bond length. Okay, now here if bond length decreases, okay, bond length decreases, the bond order increases. Okay, this you have to remember. Next is the magnetic nature. If all molecular orbitals in a molecule are doubly occupied, the substance is diamagnetic. Okay, repelled by magnetic field. Now, if the molecular orbital is completely filled, doubly occupied means completely filled. Okay, if they are completely filled, they are said to be diamagnetic. Diamagnetic means they are repelled by the magnetic field. However, if you have one or more than one molecular orbital singly occupied, that means half filled or partially filled. Okay, if there is an unpaired electron in the orbital, okay, that means you have a paramagnetic molecule. That means the molecule is attracted by magnetic field. For example, is your O2 molecule. Okay, this is what your magnetic nature is. Now, bonding in some of the homonuclear diatomic molecules. Now, how you will do some of the bonding concepts. Okay, first one is hydrogen molecule they have given. Okay, now it is formed by the combination of two hydrogen atoms, as you know. Now, each of the hydrogen atom, one electron from 1s orbital is taken. Yes or no? In each of the hydrogen atom, one electron will be donated by each of the hydrogen molecule. So it will be sigma 1s molecular orbital. So electronic configuration of hydrogen will be sigma 1s2. Why sigma 1s2? Because both of the electrons are present in the bonding molecular orbitals. There is no electron present in the antibonding molecular orbital. So it will be sigma 1s2. Now, the bond order of H2 molecule. How you will calculate the bond order? Number of bonding molecules 2 electrons are there in bonding molecules minus 0 electrons are there in antibonding, divided by 2. So it will be 1 bond. Okay, so the bond order will be 1. This means the two hydrogen atoms are bonded together by a single covalent bond. Now the bond dissociation energy of hydrogen molecule has now this bond dissociation energy and bond length, they are calculated earlier. You don't have the process or method of calculation here. Since no unpaired electron is present in hydrogen molecule, therefore it is diamagnetic. So you can get questions on these molecules also. Now similar for helium. Now for helium, what will happen? You have 1s 2 electrons in both of the helium molecule. So in this format, what will be the electronic configuration for helium? Total how many electrons? Total 4 electrons are there. So 2 electrons in your 1s bonding molecule, okay, and 2 electrons will go to your 1s antibonding molecule orbital. So your electronic configuration will be 1s2 sigma 1s2 sigma star 1s2, because total 4 electrons are there. You have to distribute all the 4 electrons. Now, what will be the bond order? It will be number of bonding molecular orbitals 2, number of antibonding molecular orbitals 2, divided by 2. So overall you will get a 0. So therefore helium molecule, it doesn't exist. H2 molecule doesn't exist because it is unstable. Okay, since you have a 0 order bond order, as I told you earlier, if you have a positive bond order, that means your molecule is stable. But if you have negative or a 0 bond order, that means your molecule is unstable. Similarly for beryllium molecule also, beryllium Be2 also. What is beryllium? It is atomic number is 4. 4 atomic number means overall you will have 8 electrons, right? So 1s sigma 1s will have 2 electrons, sigma star 1s will have 2 electrons, total 4 electron here. Again sigma 2s2 has 2 electrons, sigma star 2s2 has 2 electrons, again 4 electrons, total 4 8 electrons. So all these will cancel out. So beryllium 2 or Be2 does not exist because of its 0 bond order. Now again lithium. Now lithium, your atomic number is 3. So how many electrons total? 6 electrons. Now if I distribute this 6 electrons, so we will have 2 bonded molecules, that is sigma 1s2, sigma 2s2 and sigma star 1s2, that is 1 anti-bonding and 2 bonding electrons. The above configuration is also written as kk sigma 2s2. Now when you have sigma 1s2 and sigma star 1s2, when you have these two, we call it as a kk configuration. Okay, so you can write this as kk sigma 2s2. Okay, kk represents the closed k shell structure, that is this is your closed k shell structure. Now if I want to find the bond order, how will be it? So bond order is equal to number of bonding. Total 4 electrons are involved in bonding, right? 4 minus how many? 2 are there in antibonding, divided by 2. So it will be 4 minus 2, it will be 2. 2 ones are 2 ones are. So it will be 1 is the bond order. Okay, it means lithium 2 molecule is stable, and since there is no unpaired electrons, all the molecular orbitals are paired, it is diamagnetic. Okay, now similar for carbon. Okay, carbon and oxygen molecules, similar things are there, but here in oxygen you have to remember that there is unpaired electrons are seen. For carbon there is no unpaired electrons, so it is diamagnetic. But whereas in oxygen you can have an unpaired electron in 2px and 2py molecules. Okay, so in this case your molecule will be paramagnetic. Okay, so oxygen molecule should be paramagnetic, a prediction that corresponds to experimental observation, and this is experimentally also observed that oxygen is a paramagnetic molecule. Now these are some other examples. Now, next is your hydrogen bonding. what is hydrogen bonding? Nitrogen, oxygen and fluorine are the highly electronegative elements, as you know. Now, when they are attached to a hydrogen atom to form covalent bond, the electron of the covalent bond are shifted towards the more electronegative atom. Now, this partially positively charged hydrogen atom forms a bond with other more electronegative atom. So when you have a hydrogen atom covalently attached to the more electronegative atom, okay, so what will happen here? If you have HF, okay, what happens in HF? Fluorine being highly electronegative, the electrons will be shifted more towards the fluorine, so hydrogen will have a partial positive charge. Yes or no? Because the electron from hydrogen is also pulled towards fluorine by fluorine, because fluorine being highly electronegative, it will pull the electron towards itself. Now this bond is known as hydrogen bond. So this hydrogen, it tends to form. So here what will happen? Hydrogen will get a partial positive and fluorine will get a partial negative bond. So what will happen if you have another HF bond? Again it will have a partial positive and partial negative bond. So this hydrogen will form a bond with the this fluorine, because this is partially negative and this is partially positive. Again, if I have one more HF, okay, with partially positive and partially negative, this hydrogen will again form a bond with this. Now these new bonds which are formed, these dotted bonds which are formed, okay, these dotted bonds which are formed, they are known as hydrogen bond, and this hydrogen bond is weaker than your covalent bond. For example, HF molecule. The hydrogen bond exists between hydrogen atom of one molecule and fluorine atom of the another molecule. It is not between the same molecule, it is between different molecules. So hydrogen atom of one molecule and fluorine atom of another molecule, they are bonded together. Now here hydrogen bond, they act as a bridge, okay, it acts as a bridge between two atoms, which holds one atom by covalent bond and other atom by hydrogen bond, okay. So it acts as a bridge between two HF molecules, where one of the HF molecule is held together by covalent bond and another HF molecule is held together by a hydrogen bond, okay. Now hydrogen bond is represented by a dotted line, while the solid line represents your covalent bond. So here this solid line, it represents your covalent bond, whereas your dotted line represents your hydrogen bond. Thus, hydrogen bond can be defined as the attractive force which binds hydrogen atom of one molecule with the electronegative atom, that is fluorine, nitrogen or oxygen of another molecule. So what is hydrogen? Hydrogen bond, it can be defined as the attractive force which binds the hydrogen. Now here, to form an hydrogen bond, hydrogen is compulsory. Only with the presence of hydrogen, you can form a hydrogen bond. So hydrogen bonds, they are formed between hydrogen atom of one molecule and electronegative atom of the another molecule. Now, causes of formation of hydrogen bond. Now, when hydrogen is bonded to strongly electronegative element, the electron pair shared between the two atoms moves far away from the hydrogen atom. As I told you in the HF molecule ka example. Fluorine being highly electronegative, the electron which is shared by hydrogen is pulled more towards the fluorine molecule, and hydrogen, it feels less of its electron affinity. As a result, the hydrogen atom becomes highly electropositive with respect to other atom, that is your highly electronegative atom. Since hydrogen ka electron is pulled towards the electronegative molecule, what will happen is this pull will make hydrogen highly electropositive. Since there is displacement of electron towards X, the hydrogen acquires a fractional positive charge or partial positive charge, okay. Since there is an electron shift towards the highly electronegative molecule, hydrogen becomes highly electropositive and it attains a fractional positive charge or partial positive charge, okay. While the other molecule, electronegative molecule or X atom, or for example fluorine molecule, will attain a fractional negative charge. Now this results in the formation of a polar molecule having electrostatic force of attraction, which can be represented as, so this is what we can represent the formation of molecule as. Both with partial positive and partial negative, they will attract each other. Now the magnitude of hydrogen bonding depend on the physical state of the compound. Now to what extent the hydrogen bonding can happen, that depends upon the physical state of that compound. It is maximum in solids and minimum in gaseous state. So maximum of hydrogen bond is seen in solids, whereas minimum is seen in gaseous state. Thus hydrogen bonds have stronger influence on the structure and properties of the compound. So since it has more it has maximum in solid compounds, it will lead to the strong influence on the structure and properties of that compound. Now types of hydrogen bonding. You can have a intermolecular hydrogen bonding and intramolecular hydrogen bonding. Now what is intermolecular hydrogen bonding? It is formed between two different molecules of the same or different compounds. Okay, for example, hydrogen bond in case of HF molecule or alcohol or water molecules. Okay, in this case what happens? The hydrogen bond is formed between two different molecules of same molecule. Okay, for example, HF. Between two different HF molecules. HF. So this is what intermolecular hydrogen bonding is. What is intramolecular hydrogen bonding? It is formed when hydrogen atom is in between the two highly electronegative, that is FON atoms present within the same molecule. For example, O nitrophenol, the hydrogen is in between the two oxygen atoms. Now what is intramolecular? Intramolecular means the hydrogen bond which is formed in the same molecule, not like two molecules are combining. It is the same molecule. In the same molecule only there is a hydrogen bond which is formed. For example, is your orthonitrophenol molecule. Here what happens? The hydrogen is present between two oxygens. So this bond is not there. Initially the molecule was like this. Okay, the molecule was like this. There was no bond between this hydrogen and this oxygen. But since oxygen is highly electronegative, and this oxygen is also highly electronegative, what will happen? Here this oxygen and hydrogen has a bond between them, right? And this oxygen is highly electronegative. What will happen is this hydrogen ka electron will be pulled towards this oxygen, and this oxygen will attain a partial negative and this hydrogen will attain a partial positive charge. Now since this hydrogen has a partial positive charge, what will happen is it will pull this oxygen towards itself and form a hydrogen bond between them. So this is what intramolecular hydrogen bond is. And intermolecular means between two different or same molecules. Okay. So this is what our chapter is. So in today's video we have seen about the molecular orbital hydrogen bonding. Okay. So with this we have finished with the chapter chemical bonding and molecular structure. So thank you for watching my video. Please do like, share and subscribe to our channel.